comparisons. Alright, welcome back everybody. Let's get right into it. So today we are going to be covering comparisons. The current state of the compiler is that we have global variable declarations, we have assignments, and we have variable instances so that we can use them in binary expressions. This is an example right here. This is what we compiled last lecture. And today we want to add comparison operators to our compiler. And why not add single line comments while we're at it, because might as well. So what we're going to have to do is we're going to have to add in comparison operator tokens for all the common ones. We're going to have, we'll see the list in a second. We need to add precedence values for them. We need to update our scanner so that we can look ahead at the next character, because we now have tokens that are prefixes of other tokens. And so we want to make sure that we don't confuse a single equals for a double equals or vice versa. And then same thing with less than and greater than. We're obviously going to generate our LLVM comparison code. And then we are going to add in some LLVM logic to extend and truncate our virtual register contents, because the compare function that we're going to be using in LLVM returns I1s, which are Boolean values, instead of I32s, which is what we've been using so far. So, sorry, I just want to make sure. Got a question. Okay. And actually, I'm gonna pull up this on YouTube so I can see the comments. All right. All right. Cool. So these are the new tokens that I've added. We've got. Hello.
How much did that miss?
Not too much. We're covering comparisons today. So these are the tokens we added. We added in. Sorry, this should be two equals signs. I'll fix that when I re-upload the lectures. So that's a double equals. Compares if two numbers are the same. Not equals. We've got a less than. We've got a less than or equal. And then we've got a greater than or equal. Notice their precedence values are different, so they're going to be computed in a different order. The first thing I want to go over is comment scanning, because it's pretty easy to do. So let's go into our scanner. Alright, there's you. Alright, so down in scan. So I said that we have to look ahead at the next character, right? So what we're going to do is we're going to grab the next character. This should be a next char, not a skip, but I'll fix that. So the way we're going to use this is that now, when we call from string, we also give the next character in the input stream. And we can see how that gets used in from string. So this is kind of a temporary tactic that we're going to use. There's a smarter way we can go about it in the future that we probably will, unless I decide not to. I mean, I think it's kind of up in the air right now. But so if the current token is an equal sign and the next token is also an equal sign, then we're going to say, that's an equals token, not an assigned token. I've got this short circuit thing here. It's just, I don't know, I thought short circuit made sense. It's going to short out this method. If we find a short circuit token, and there's a next char in the, and it's not an empty next char, then we're going to put back the character. Sorry, if there's no short circuit token and there is an next char, we're going to put the token back into the stream so we can scan it properly next time. Otherwise, we don't want to put the character back because we just scanned it, and we're going to return this new next chart token. And so we've got a case here for anything where there's a prefix token. So a sign is a prefix of equals. Our eventual not token that I haven't added yet, but we will eventually, is a prefix for not equals. Less than is a prefix for less than or equals, and greater than is a prefix for greater than or equals. So after that, it's just our regular run-of-the-mill scanning. And you can see that when I invoke it, let's see. When I invoke it here, I do give the next character, but when we have an identifier, we are going to give it a null value because we just scanned in the entire identifier and we confirmed that it is the whole shebang. So we don't want anything after it being processed. And then that also lends itself to single line comment parsing. So if we just find that the current and next character are 2 slashes, then we are just going to, as long as there's not a new line character, we're going to grab the next character. So that'll process all the characters up to the end of the line. And then we are going to do, so it's a recursive call, so it's not great, but it's really only not great if there's like 100 single line comments in a row, which I would hope there aren't. You might think that eventually this is bad because when we process string literals, that might throw an issue, but string literals, like identifiers, are going to be processed in their own function, so this should not collide with them. So next thing I want to go over, talked about that. Okay, so we have an issue. When we look at the LVM reference manual and we look at once it loads, the integer comparison instruction, we notice that it returns an I1. That's short for a single bit wide integer, so that can only be a 0 or 1, considering that all we have right now is unsigned integers. But our entire LLVM generation is built around I32, so we have them hard-coded everywhere. So we need to modify all that code so that we can support more types in the future. This is one of those times where you're going to have to rewrite a bunch of code. I think I gave you all a heads up on that. But so to aid that modification, inside of the LLVM value class, although I should move it eventually, I have added a number type class. So this is another enum object that just encodes information about various data types that we will use throughout the course. I added all of these right now, although we are not going to cover how to support them in this lecture, because that'll be the homework. We've got this enum name, and then we map it to its LLVM representation. We have a byte width, which just converts it into the number of bytes that it supports. Or yes, I might have got mixed up there. Might be bit width. I don't know. Not important. No, it's byte width because it works. I checked it. It works. You don't have to worry. It's fine. But I will look at that. I'll make sure it's correct. We have a from int function that is just going to make sure if you give it an int, if you give it a 1, it'll give you a bool. If you give it an 8, it'll give you a char, etc. We give it a string value. This is how we can compute its int value. And you'll notice that for LLVM value, those now have number types. They default to int so that we don't have to rewrite stuff everywhere. But in a few places we do have to explicitly say, I want to put an int right here. The other place we have number types is in our global symbol table. So global symbol tables have to hold on to the data type to make sure that you don't do anything dumb, like try to store an integer value into a Boolean variable. So one thing is that, in C there's no actual Booleans, so it's up to you whether you'd like to add those in, but I think they're helpful, and I don't know. They act like regular integers anyway, so it's not really a big deal. So let's see how this messes with our LLVM code. And right here, I'm actually going to just, those don't work. You have to use the slots on the floor. Right here, I'm just going to compare to the old version so that we can very clearly see exactly what lines we changed. Oh, that's not what I want. To compare it to last branch. Alright, so this is LLVM.py. We can expand some data here. So this is our ensure registers loaded function. So before we were just assuming that we had I32s, but we were given a list of LLVM values, so we should use those LLVM values number type to get the proper representation, because we might have bools from now on, or shorts or something. Not going to go over int resize yet. So for all of our arithmetic functions, our add, subtract, etc., again, those took in LLVM values already, so I replaced the I32s with number types. That's mul, that's division. This is resizing, I'll come back to that. That's comparison, I'll come back to that. Our store function, there's one other change that I'll get into, kind of a bug fix that I'll talk about probably later. LLVM store global, I had to change it from an R value register to an LLVM value. And we'll go back into translate.py to see that we also changed the input types of AST to LLVM. But now, when we're storing a global, we check its number type, because, again, we want to make sure we're not storing the wrong data type in there. And then we do the rest, regular stuff. And I forgot to replace those I32s. I'll fix that. LVM stack allocation, again, I32 changes to a number type. And that's what we got for that. So just generally replacing all I32s with number types. Oh, no, I remember why I didn't replace the I32s here. Because, I still should change them, but my logic was that we don't have non-integer variables yet, so we don't need to replace them. But you should replace them. That's the good thing to do. I'm going to stay on this diff checker. So now we have an issue where if we look at the example that we want to compile today, so let's go to desktop echo. Oh, I think I might have changed it, but let's see if I didn't. Okay, yeah. So we've got an int x, and we want to assign it to the value is 7 greater than or equal to 7. But 7 greater than or equal to 7 is an I1, and x is an I32. So there's an issue there. And the solution is that we can extend the I1 to a longer width data type. And in other scenarios, we could truncate an R value to fit into an L value. Although that's, if a programmer is doing that, they should probably be doing something else. So, but I added the logic for it anyways in case I needed it. So this is the LLVM int resize function. So it's going to print out something I shouldn't have closed that terminal. Oh wait, I didn't. It's going to spit out scripts run examples test 1. So this is a extension function or command. So what it's going to say is 0 extend, and I'll explain what that means in a second. This register, which is an I1, into an I32, and then store it into this new register. So 0 extension means just pad zeros onto the left of the bit representation of the number. LOVM also offers a signed extension function, which we're not going to use yet because we don't have signed numbers, but that has a bit more wonky behavior, so we shouldn't use it yet. We should just use 0 extend. But truncate, the truncate command has the same syntax, so we can just determine, hey, is this new width bigger than the old width? Then we should extend, otherwise we should truncate. And again, get another local virtual register, print out all our junk. This is guaranteed to be a loaded register, so we're good there, and we will return the latest loaded register. And so let's see all the instances of where we used LVM in resize. So, in binary arithmetic, if eventually we have a short and an integer and we want to add them together, we should check if their number types don't match, and if they do, we should resize. In this case, we always want to extend, which is why I have 2 if statements for which direction the inequality is going in. But again, in some cases we will want to truncate. LVM comparison, we'll talk about that in a second. Again, we resize whenever we're storing a global. And so that's it for that part. Alright, so now let's talk about generating comparisons. So that iCompare integer comparison function is super nice because it has the same syntax, and you just plug in which comparison you want to do. So this means signed less than or equal to. We've got equal, not equal, signed less than or equal to, signed greater than, and signed greater than or equal. So these map directly to our tokens, which is really nice. If you go look at ACWJ, I don't think x86 had, at least in his implementation, x86, he didn't use one-to-one mappings like this. He had to invert the not equals and stuff like that. So this is a nice feature of LLVM. We're going to get the appropriate operator from this operators list, and then we are going to just generate this line. Set a register equal to iCompare of our comparison operator, and then we give it the values, the number type of both of our values, followed by the values themselves. And again, this is guaranteed to be loaded, so we append it to loaded registers, and then we return it. And let's look at AST to LVM, because there's a little bit of a change. Again, so changed our value register to an LVM value, so that we can make sure that on the right side of an assignment we have the same data type as we have on the left side. We changed this 0 into the none version of LVM value type, which is a much better way to prevent errors, because 0 is a valid virtual register in LVM, but LVM value type.none is not a virtual register. So that's a good little thing we did right there. I started adding comments because it was getting kind of messy. We see that if we have a comparison operator token, we are just going to ensure that the registers are loaded, and then we're going to call that LVM comparison function. So nothing crazy there. Again, replacing our old R value stuff with our new R value stuff. And when we call AST to LVM, we are going to pass in a none value type. So, I mean, okay, one thing, I'd like to emphasize how cool LVM is, because we wrote like maybe 50 lines of code, and a lot of that was like boilerplate, and our language, which previously was just arithmetic, now has this, completely logically based math chunk that it didn't have before. We didn't really have to do a whole lot of hard stuff when it came to messing with data types. It was I think a fairly simple expansion of our compiler. So I think LVM is really cool for that. I'm going to go over the optional homework, and this is a pretty short lecture, so I'd like to walk around and see y'all's compilers and maybe help with any issues that you might have. So first, to go over the homework, I would like you to parse and generate code for the remaining integer types, except for char, because we're going to do char together, because it's, just a little bit more complicated. And I changed my mind on bool, so you don't have to do bool. I'll fix the slides and I'll re-upload them. So I want short int and long tokens. Don't worry about long or unsigned long or long int or anything like that. Just short int long. Your compiler should enforce that assignments to these types fit within the type's range. So if a programmer tries to assign 65,536 to a short, which is 2 out of its range, there should be an error thrown. And of course, when if you have like long x and then x equals 1, the current logic says that integer literals are int types, so they're 32 bits wide. So you'll need to make sure that when you're assigning, you need to expand. But again, if there's a truncate error, just throw an error. Don't assign, because that's more like hidden meaning that our compiler does that we don't really want. We want our programmer to know exactly what they're writing. Your generated LLVM should use I16, I32, and I64 for the widths of each of these types. That includes declarations, assignments, Boolean expressions, etc. And again, for assignments, you must, again, change my mind on the truncate. Just extend R values and throw an error if you try to truncate. LLVM is going to enforce this anyways. It's not going to let you assign an I1 to an I8. It's not going to let you assign an I8 to an I1. So it's going to make you truncate or extend. And actually, so with the truncate stuff, there is something I did in purple that you might be interested in. What I did is whenever I would scan in an integer token, I added tokens for short literal and long literal. And what I did was whenever I parsed an integer literal or a number literal, I would find the minimum data type that I would need to store that value, and that would keep me from ever truncating, and it would just always have extensions, so stuff would just always get extended, which I think is a little neater, and again doesn't have as much undefined behavior. So this homework compared to the last ones is fairly hard. It's going to be more work, but I think it's a lot more interesting, and you're going to feel more accomplished at the end of it, because this is something that a language should have. At least a C-like language should have multiple integer types like this. One cool thing about LLVM that I think I mentioned in the first lecture is that you don't have to use a power of 2 in those I chunks right there. You can put any number you want, and it will let you make an I-45 or an I-90 or something like that, which is very interesting, and it's going to abstract away all that logic for you. So we don't have to worry about any of that binary stuff. It's going to worry about that for us. So So that was just a little fun tidbit. So that's a big one, but I think it's a lot of fun. Let me check the Discord to see if there's any questions. Nope. Okay, well, that concludes this lecture. Thank you everybody for coming, and have a good one.